Okay, let's unpack this. We are diving deep into a topic that feels a bit like the holy grail of modern AI research.
It really is.
How do you get the specialized power of a massive, expensive language model into something small, affordable, and, incredibly efficient?
Exactly.
For you, the listener who follows the space, you know the landscape. The big players, these massive large language models, LLMs, think GPT-4 are undeniable heavyweights.
Phenomenal generalists.
Absolutely, their zero-shot capabilities are amazing, but let's be real, they come with a hefty price tag. We're talking computational resources, memory, energy.
And if you want to use them for specific, niche, high-volume tasks, that cost just adds up so fast.
And that's the core conflict, right? Efficiency versus specialization.
You've got your small language models, your SLMs, which are quick and cheap to run, but they usually lack the deep domain expertise you absolutely need for critical fields.
Like medicine or legal analysis.
Or advanced scientific research, yeah.
Mhm.
So the mission of the research we're looking at today wasn't just about an incremental improvement. They were looking for a fundamental shortcut.
And they found one using this novel method, LLM-based generative data augmentation.
Which is a fancy way of saying they had the biggest, smartest models create a highly specialized study guide for the smaller ones.
And here is the punchline we have to deliver right up front, because it just fundamentally changes how we think about deploying specialized AI.
Okay, lay it on us.
A specific SLM, one with under 1.6 billion parameters, was fine-tuned using this exact method.
Right.
And when they tested it on this really stringent medical question-answering dataset, PubMedQA, it didn't just compete with few-shot GPT-4.
Don't leave us hanging.
It outperformed it.
Wow, okay. That is a staggering claim. A tiny model, a computational featherweight, beats a heavyweight champion in a specialized domain.
That's what we need to unpack today. How on earth did they pull off this computational sleight of hand?
Let's start with that fundamental challenge. If you're, say, a major hospital system running a 175 billion parameter model.
Like an API call to GPT 3.5 Turbo.
Exactly. For every single diagnostic query or research question, it's just prohibitively expensive, and honestly, it's often overkill.
Right, but you still need that specialized knowledge that the generic models just don't have.
Precisely. So the goal was to adapt the SLM to this niche medical domain without having to, train the entire architecture from scratch.
And this is where efficient fine-tuning techniques come into play. They let you adapt the model without updating all of the model's weights.
That's it. And they focus primarily on two methods, prefix tuning and low-rank adaptation, or LORAR.
Okay, these sound very technical. Can you walk us through the difference? Help us visualize what's actually happening inside the machine.
I can try. So think of the large language model as this massive complex engine. You needed to start driving on a very specific, narrow road, the medical domain.
I'm with you.
Prefix tuning is kind of like adding virtual tokens or continuous prompts to the model's input. Imagine you're putting these highly specific, temporary sticky notes at the beginning of the engine's manual every time you ask it a question.
So you're trying to adapt its behavior with instructions at the input.
You're optimizing those temporary instructions to make the engine respond differently, but you're not touching the engine itself.
So adapting the interface, not the engine. What about LoRa?
LoRa is much more fundamental and, as it turned out, much more stable. If the main model weights are the core engine components, LoRa works by decomposing the large weight matrices into smaller, lower rank matrices. Think of them as adapter components.
Okay.
You only train and update these tiny adapter matrices. It's like installing a specialized small adapter card that connects to the main engine. That adapter learns the characteristics of the new medical data, but the expensive, massive engine block, it stays completely untouched.
That analogy helps a lot. It sounds like LoRa is actually integrating the knowledge structurally, while prefix tuning is just trying to steer it from the outside.
That's a great way to put it.
So which one proved more robust in their tests?
LoRa was the clear winner. They tested both on BioGPT Large, and LoRa showed this remarkable stability across a huge range of hyperparameters. They tested rank values from 16 all the way up to 512.
And in practical terms, what does that stability mean?
It means LoRa consistently gave good results, whether they fine-tuned it aggressively or gently. It's the difference between a reliable tool and a fragile one.
And prefix tuning.
It was so sensitive. If you change the range of virtual tokens even a little bit, performance could just drop off a cliff. For a researcher, that stability is everything. You spend less time worrying about finding the one perfect setting.
And more time actually applying the model.
Exactly. So LoRa was selected as the default because it's just the most predictable and reliable adapter.
Okay, so before they even got to the main event, the augmentation, they needed a performance baseline.
Right, they tested 3 common small language models on the raw PubMedQA dataset.
Yeah.
We had BioGPT Large, Llama 7B, and then Alpaca 7B.
Alpaca 7B is the instruction-tuned version of Llama 7B.
Correct.
Now, here is where we hit one of the first genuinely surprising insights of this deep dive. Because in the current AI zeitgeist, right, instruction-tuned models like Alpaca, they're supposed to be superior.
We assume they are, yeah. They're trained to follow explicit human instructions better, so you'd think better instruction following leads to better results.
And yet, what we saw in the baseline test was the complete opposite.
It seemed like the instruction tuning actually constrained Alpaca 7B's ability to adapt to this new, highly specific domain.
Compared to the naive Llama 7B model it was derived from, that just seems totally counterintuitive. Give us the specific numbers.
So when they tested it on the original non-augmented PubMedQA data, Alpaca 7B achieved a pretty paltry accuracy of 0.380. The simpler pre-trained Llama 7B model, though, it achieved a significantly higher accuracy of 0.594.
Wow. That's a huge drop-off. So if I'm a researcher trying to build the best specialized medical model, starting with the instruction-tuned version, it actually handcuffs me.
That is the profound implication here. We often think of instruction tuning as purely a good thing. It improves conversational quality.
Right.
But this suggests that when a model optimizes too aggressively for general-purpose instruction following learning stylistic rules, conversational norms, it might actually sacrifice its raw potential for deep domain adaptation.
So it lost its semantic flexibility in favor of, what, polite obedience?
That's a perfect way to describe it, yeah.
This is a major insight for any developer building these kinds of specialized SLMs. Maybe stick with the raw, pre-trained power source, not the conversational filter.
And that finding sets the stage perfectly for the core innovation here, generative data augmentation.
Right. The original PubMedQA training set was tiny. Just 450 samples. That's not nearly enough to train a model to truly master a complex medical domain.
Not even close. So they used the massive power of LLMs to scale that data. They leveraged 2 different ones, GPT 3.5 Turbo and GPT-4, to bulk up those 450 samples in 2 different ways.
The first was a pretty low-risk approach, right?
Yeah, that was rewrite QAA, simply rewriting or paraphrasing existing question-answer pairs to add stylistic diversity.
And the second, high-risk, high-reward approach.
That was new QA, instructing the LLMs to generate entirely new, novel question-answer pairs based on the training data's structure and context.
This is where they tried to teach the smaller models new facts by having the big models make up high-quality, specialized homework questions.
And this is also where we learned a very harsh lesson about data quality. Because if the generator doesn't have the domain knowledge, even a powerful LLM can just output garbage.
And that's exactly what happened. We saw a definitive flop.
A total flop. When they used GPT 3.5 Turbo, which is an impressive generalist, but it lacks that deep, specialized medical knowledge of GPT-4 to generate those entirely new QA pairs.
The performance of the fine-tuned SLM actually went down.
It went down. The smaller model was being trained on noise. It's like they were given 1,000 pages of high-quality photocopies mixed with 1,000 pages of plausible-sounding medical fan fiction.
So the data quality was so poor, it degraded the model's performance. It actively confused it.
Exactly. But the success came when they switched to GPT-4.
The model with superior domain-specific knowledge.
Right. Instructing it to generate new training data resulted in a highly significant, measurable improvement in the performance of the smaller models.
And that is the essential takeaway for everyone listening. LLMs are fantastic for refining and diversifying data. Paraphrasing existing facts is fine.
Absolutely. But to create high-quality, novel, domain-specific data that genuinely improve downstream performance, the source, the augmenting LLM, it must already possess the deep, specialized domain knowledge you are trying to instill.
You can't synthesize expertise from thin air.
You really can't.
Which brings us to the exciting culmination of the experiment, the performance payoff. We saw the stability of LoRa, we avoided the trap of instruction tuning, and we used high-fidelity GPT-4 generated data. Let's focus on the results of that best configuration.
The top results came from, well, the perfect storm, BioGPT Large.
The SLM that already had that foundational domain-specific pre-training?
Right. Fine-tuned using the LoRa technique and fed the new data that was augmented by GPT-4.
Okay, let's talk about the specific accuracy figures again, because this is the money shot. This validates the entire approach.
Okay, so the resulting BioGPT Large SLM with under 1.6 billion parameters, achieved an accuracy of 0.754 on the PubMedQA test set.
And what was the score for the generalist heavyweight, GPT-4?
Few shot GPT-4 specifically, the 5-shot configuration, which gives it 5 examples to help it answer. It achieved an accuracy of 0.744.
So it beat it. The 0.754 surpasses the 0.744.
It beat it.
That is staggering. You have a model that is orders of magnitude smaller and cheaper to run, yet it is demonstrably better at the single specialized medical task than one of the world's most advanced AIs.
Even when that AI has 5 examples in its prompt to guide it.
And we should also point out, just for contrast, how important the augmentation was. This finished SLM is twice as accurate as the zero-shot GPT 3.5 turbo baseline, which was, what, 0.372?
That's right. The efficiency gains here are just immense. Think of the real-world application. A specialized SLM running locally on affordable infrastructure in a clinic.
Instantly answering medical questions.
With higher accuracy than a constant, expensive API call to GPT-4, they created a bespoke, highly effective, lightweight expert.
And we absolutely can't overlook the power of the initial pre-training, which we touched on. BioGPT consistently outperformed LLM-7B.
Even when both were fine-tuned on the superior GPT-4 augmented data, and that consistency is key.
Why?
BioGPT's pre-training, its exposure to vast quantities of biomedical text before the experiment even began, gave it the foundational vocabulary. It had the grammar of medicine.
So when the high-quality specialized augmented data arrived,
BioGPT was able to absorb and leverage that data much more effectively than the purely general-purpose LLM-7B. It reinforced the expertise it already understood, and that led to the winning performance.
So synthesizing everything we've found, this research successfully demonstrated a viable, reproducible blueprint for developing specialized AI. You start with the domain pre-trained SLM, use the efficient LoRa adapter technique, and feed it high-quality, newly generated data sourced from the very best generalist LLM.
That is the precise formula. Generative data augmentation successfully bridges that gap between computational efficiency and specialized performance.
But with a huge caveat.
A huge one. Only if the augmenting LLM acts as an expert source, not merely a data multiplier.
And looking forward, where do the researchers suggest we go next to enhance these specialized SLMs even further?
They mentioned a couple of powerful AI techniques. 2 main avenues stand out. First, they want to investigate knowledge distillation.
Which is a fascinating concept.
It is. You're training a smaller model to strictly mimic the output and behavior of a much larger, more powerful teacher model. So instead of just using GPT-4 to make study material, you train the small model to answer questions like GPT-4.
It's like trying to upload the big model's learned intuition directly into the little model's brain.
Exactly. And the second approach is applying contrastive learning.
Okay.
By using contrastive learning, they would specifically train the SLM to better differentiate, to identify similarities and differences between highly specific medical data instances, like comparing case files or differential diagnoses.
Which would improve its ability to generalize accurately to new and unseen medical scenarios.
That's the idea.
This research has fundamentally challenged the prevailing notion that bigger is always better, at least in specialized AI.
And this raises an important question for you, the listener, to consider as you watch this field evolve. If the primary high-value function of the most advanced LLMs, like GPT-4, can be captured by using them purely as data generators and knowledge refiners,
as tools to train much smaller, cheaper, and faster models,
then does the computational future of AI truly lie in continuously building massive, monolithic, billion-dollar LLMs, or will we see a proliferation of countless hyper-specialized, highly efficient SLMs, each an expert in its own narrow critical domain?
That's the balance we are about to strike.